Hey guys, welcome to Objective 2.4. Create and implement a class hierarchy. Today's objectives cover design and implement interfaces, create and use base classes, and use some of the standard .NET framework interfaces. So, the first section that the book starts with is, like I said, designing and implementing interfaces. But I quickly want to just go over the idea of what inheritance kind of brings to the table, because this is what we're really talking about. And in the most general way, I just want to say that, inheritance allows us to establish the idea of an is a relationship. And when we use inheritance and create is a relationships, basically what that's saying or doing is that whatever class, whatever derived class that is derived from a base class, is essentially the base class. So what I mean by that, just put it in perspective, if we have, let's say, an animal class, and then a dog class that derives from that animal class, that means a dog is a animal. And that's where the is comes from. So essentially, in that kind of situation, anywhere that I had an animal, maybe it's a parameter for a function or something else, I could replace that with a dog because a dog is an animal. Because the dog inherits all of the characteristics and traits of the animal, logically we can think of it as the dog is an animal. So that's where the is a relationship comes into play. Okay, so now with that aside, let's go ahead and jump right into designing and implementing interfaces. So an interface is basically a guideline for some class or struct to follow. So, for example, if I create an interface, let's say I test. Let's say my interface is called I test. By the way, there is a convention in C# that naming interfaces, you should normally start with a capital I so that you can just quickly tell that the thing is an interface. So let's say we had an example of an interface called I test. I test would contain function prototypes or just the signature of a function. So let's say we had a function that said get result and returned an integer. We would just say int get result and then it's pretty much semicolon. And that's just the function header. And that goes into the interface. And any class that I attach this interface to has to follow those guidelines, meaning that that class must implement a function called getResult that returns an integer. It's pretty much a guideline or a contract. And I'll talk about the idea with the contract in a little bit. But yeah, you can think of the interface as a contract. It's what anything that implements an interface must follow the guidelines of the interface. So let's go ahead and just create an example of this. So let's go ahead and create, let's go to my Solution Explorer, and I'm going to create an interface. So I'm going to go to New Item, and I'm going to create an interface, and I'm going to call this interface iExample. Inside my interface, I'm going to list the possible things that we could put into an interface, which are functions, properties, events, and indexers. So I'm going to create a function, get result, which returns a string, int value, which is a property, event handler, results retrieve, which is a event, and then an indexer. Get set. So this is our basic interface and 4 members that are in this interface. Now, if I create a class and that implements this interface, that means that that class is required to implement all the requirements of this interface. So all 4 of these members. So let's go ahead and create a class that will do this. Add class, and I'll call it example implementation. So now in my example implementation, I'm going to implement the iExample interface right there, iExample. Now, because I implemented this, if I try to compile and run this, you see right away we're getting errors. And it's saying that our example implementation class does not implement the interface member, get results, etc., etc., etc. So basically what it's saying is, this is breaking the contract. So I can just right click on iExample and hit implement interface, and this is just a shortcut. You can implement the interface implicitly or explicitly. I'm sure we'll go over explicit. Actually, did I already do that in a previous lesson? I don't know. But we're just going to implement the interface regularly. And by doing that, it creates all the requirements that we need to satisfy this interface. But for things that require us to actually put some code into it, it automatically just throws a not implemented exception. So we have to write the implementation for get result, value, and index. We would have to write all this implementation. And just for some sample data, I could just write return result for this one. For our value, we'll just make it into an auto implemented like that. And then for this string index, I don't know. I'm looking at the book right now. This is what the book's doing. And they just returned 42. Basically, this doesn't really matter. Essentially, what they're trying to show you is that now we implemented all the requirements of this interface called iExample, which we're going to go a lot more into interfaces. It's just a quick introduction. Now, if I try to compile this, I still have an error. What is the error? Oh, set. I need a set. Okay, set does nothing. If I compile this, as you can see, we get the rebuild all succeeded. So this compiled fine because this class is satisfying all the requirements of iExample. This is our contract, I guess you could say. Another note, in the interface definition, we do not specify access modifiers on any member because by default, all members are public, so we do not specify an access modifier. Okay. Another note I want to point out is that interfaces can inherit, I guess you could say, from other interfaces. So if I have 2 interfaces, let's say iExample, and then we have another interface, iTest. If example is implementing or inheriting from iTest, that means that anything that implements iExample will now have to implement both. So what that looks like, if I have another interface called iTest, and this just has, I don't know, void do test, I don't know, some kind of function in it. If I make the iExample inherit that, like this, now in my example implementation, even though I'm just implementing iExample, iExample inherits from iTest. So that means that now iExample also has do test as a requirement, and we didn't implement that. So if I try to compile that now, we get the error. I can right click, implement it again, and we'll get the implementation for it. I mean the definition for it, and then we have to supply the implementation, but the error will go away. So yes, you can stack up interfaces, making them inherit from each other. Okay, let's go ahead and remove this, and we're going to create a different example real quick. Okay, what else? I'm going to change this around, but... So basically, an interface, one thing to think about an interface is that an interface cannot be instantiated because an interface has no implementation. An interface is simply just a definition of what needs to be implemented if you implement this interface. But the interface itself cannot be instantiated. So, example meaning I can't go example A equals new example example. I cannot do that because it doesn't have any implementation. However, this does not mean that we can't have any interface variables. Now, if we instantiate an object that implements an interface, any interface variable could hold a reference to that object. So let's go ahead and create. Let's change this interface to iAnimal instead of iExample. In iAnimal, it's going to have one required function, void move. Inside of example implementation, we're going to rename this as dog, and it's going to implement iAnimal. So to implement that, we have to implement the interface, which is public void move, and I don't know, it's not going to really do anything. I don't know. I'll just go console.writeLine move. But I'm also going to add another function just on top of that. I'm going to say public void bark, because, a dog can bark. And this will just go console.writeLine bark. But inside the interface, I did not specify a bark function. So now in my program, when I go ahead and say dog d equals new dog, if I did this, this would work as expected. Dog.bark, dog.move. If I run that, we get the bark and move. But I said I wanted to, use a variable of an interface. So if I go, iAnimal, say D equals new dog, that is perfectly fine. What this line is doing, it's saying iAnimal D, which is my variable, is pointing to some kind of dog object implementation. This dog object is floating in the heap right now, and we're pointing to it, essentially. Now, the tricky part comes if I try to go D dot. You can see that we have the move function, and I could run the move function, but we do not have the bark function. Although iAnimal D is pointing to a dog object, so there is a bark function there somewhere. We just do not see it because we're looking at the dog object through the eyes of this iAnimal interface. And in the eyes of the iAnimal interface, we only have a function called void move. So the only function that this variable is comfortable with accessing is the move function, because it's positive that it has that. Because a dog implements iAnimal, it's 100% positive that dog has this move function. So when I'm looking at dog through the eyes of the iAnimal interface, I can access that. Now, like I said before, even with this, behind the scenes, iAnimal is still pointing to a dog. So it is a dog. So if we mess around with some casting, we could still extract that bark function somehow out of this and still call bark. Now, I think I went over this in Objective 2.2, I'm pretty sure. So you can check that out if you want to figure out how to do some casting and stuff to manipulate this. Okay, let's go ahead and create another implementation. And this one will be class cat. And it implements iAnimal. And we're going to implement the same function, except we're just going to specify that the dog move and cat move, so we know which one's going on. So another example of where we can use an interface is in a function parameter. So if I had a function, let's say static void move animal, that took in an iAnimal variable, or any object that implements iAnimal. Now, because I have a dog and a cat, both of those implemented, so I could pass them in. So I can go cat c equals new cat, and then in here I'm going to go animal.move, essentially. I want to remove that from there. So in this example, I'm just going to go move animal, passing in D, and then move animal, passing in C. And because of this, we pretty much created a very generic function. This function, and this is one benefit of using interfaces. This function says I require an I-animal interface. And because of that, I can pass in a cat, a dog, a lion, anything that implements this interface called I-animal can be passed into here. Because all these animals implement I-animal, so it's guaranteed that it knows that it has the move function, so it all works. If I run this, we'll see dog move and cat move. And this is where we're sort of seeing this really idea of this interface as being a contract. And this is a pretty important concept in programming. And it's basically what you want to do is you want to try to program against contracts rather than the actual implementations. The interface guarantees that certain functionality is available, but you don't really care how it's implemented behind the scenes. A really good example of this being used is in WCF, Windows Communication Foundation, which I'm going to be doing actually a video series on soon. And basically with Windows Communication Foundation allows you to create applications that have clients and you can think of, or services, or clients and servers. And basically it allows you to write applications that, your client can interact with your server, and then your server can send information back to your client, send information to other clients, and things like that. And how that works kind of behind the scenes, well, there's a couple ways, but one way of doing it is using this, or it uses this idea of contracts or service contracts. And basically with this service contract, the client pretty much has access to this contract, but not the actual implementation of functions that lie on the service. So when a client makes a function call to the service saying get value or something to the service, it doesn't actually know what code that the service is using to get this value. It has no idea. The client is only using the service contract in order to know that it has a function that exists that's called get value. The contract just ensures that that function exists on the service, but it doesn't ensure anything or tell the client anything about how it's implemented. It has no idea. It just knows that what its method's signature, essentially. So that's what contracts are, and that's really a good way to program. Another side note about inheritance, C# does not support multiple inheritance. However, like there are some languages, like C++ is a perfect example that supports multiple inheritance, but in C# it does not support multiple inheritance, meaning you cannot derive from more than one base class. However, C# does offer multiple interface inheritance, and and basically with multiple interface inheritance, you can sort of get around and do everything the same way. Okay, so like with interfaces, like we were saying, interfaces only define the public signature. So deriving from an interface or implementing interface, you don't actually get any implementation. It's just telling you what you have to implement. So if you implement an interface, you have to write the implementation for everything that is in that interface. If you want to inherit and derive from something and get implementations rather than having to write your own, this is where you'll use inheritance that's inheriting from a base class. Okay, so let's go ahead and let's delete this stuff. I should probably just delete both the. Okay. So, for an example of creating a base class and then inheriting from a base class, I'm going to use the example from the book. Although, I mean, I don't think it's the best way to show, this idea of basic inheritance, even though it's trying to make it on a little bit more complex level. So I'm going to try to explain it the best way I can so everyone understands what's going on inside of this example. So I'm just going to first, write out their example, run it, show you what happens. Actually, it doesn't even run, I don't even think. Yeah, for the most part, it doesn't even really run. I mean, they left out implementations in it. So I'm just going to write the code and then explain what would happen and try to explain this part of it, because I don't know. I just don't like this. And there's also another part upcoming in this lesson that I don't like, again, from this author, which I'll point out, obviously, because what's in the book is actually wrong. Yeah, so I'm going to go ahead and write this all out and then explain it. Okay, so I just typed the code for you guys, and now I just want to go over it. But before I start, I just want to point out that, the main point of this is just to emphasize a couple things. The first thing is, the author used a generic example, and because of this is generic, anything that implements identity could essentially use this. Okay, that's great. And also, but the main point there they're trying to do this is that they're trying to emphasize that inheritance can help you reuse your code. If you want to, you can reuse old code, add new code, and everything. This is just a basic example of a basic class hierarchy. Now, after I go over this, I'm going to make my own simple hierarchy, and then we'll move forward. Will be pretty basic, the one I do. So, to just quickly look at this, I'm not going to go into too much detail. I'm just to maybe clear up some of the issues that you guys are having with this. I don't like this example. I don't know why it's here. Basically, so an interface is defined called identity, and the only requirement of this is that you implement a property called ID of type integer. Okay. Then we have our base class, which is repository, which is a generic class. We can see by this. And on the generic class, there's a constraint specified. This is a constraint, and it's specifying that any generic or any object that's passed into this through the generic property must implement identity. So that's the constraint right there to ensure that everything goes into here is only identity. They have a protected innumerable generic variable called underscore elements, and these are going to be the elements of whatever's passed into the repository. You can see in the constructor, the argument for the constructor is that it has to be, you have to pass in an innumerable of t elements, and essentially that is anything that implements an innumerable interface, and that is all collection types, arrays, lists, so on. Any kind of collection type. It could even be a custom thing that you implement, as long as you implement this interface. So that's being passed in and then stored into this protected variable. Protected, if you didn't know, I think I went over this in one of these lessons, it means that it's private to everyone besides the only things that can see it are the class itself and derived classes. Then we have another function that returns t, which is just whatever is passed in. Something that t is essentially anything that implements identity. And then it does a find by ID, where you type in ID, and this returns essentially what this is saying. Return the occurrence that meets this. I don't want to say query. What is it? Condition, and you're pretty much just saying whatever enters in, if an element matches that ID of whatever's passed into that, just return the element, is what this is saying. So that's find by ID. So basically, here's a way that we can search and find by ID of this repository. Now we have a class called order, which implements our entity. So this order can be used in our repository. So in our order repository, this is just a class. Now this is the class that's inheriting from the base class. So once it inherits the base class, which is right here, it gets all the characteristics of this base class. So it has this find by ID function that's built into it. But then on top of that, they added this other function called filter orders on amount. So we could filter the orders on amount, or we could filter orders on ID, depending if there was amount in here, but it was omitted in the code. The amount should go here somewhere. So we can filter on amount or ID. That's basically what's going on here. This is the constructor call, and this is calling the base constructor, passing in whatever's passed into this order repository. Okay, so that's all I want to talk about this. I don't really care for this example. I'm going to go ahead and write my own example with you guys, very basically, a really basic example to show you, just quickly explain what base classes are and inheriting from base classes, what happens, etc., as fast as I can. So let's go ahead and create a little animal hierarchy. So we're going to create a class. We're going to put all our classes into one class file, CS file. So I'll call it animal, but I'm going to put everything into here. So we have a class called animal, and our animal is going to basically have, public string name. It will have a name, public int age. So these are two things that our animal has, and maybe we'll make it public void move. It has a function that it can move. This is our animal base class. This is our base class. Now I'll implement another class called dog, which implements or inherits animal. Now by doing that, dog has all the characteristics of an animal. A dog is an animal now. But on top of that, I'm going to add in some other things. I'm going to, actually, what am I doing with this move? I have to implement it. Let's go ahead, console.writeLine. Move, animal.move. Animal.move. So in our dog now, we can add something else. I'm going to say public void bark. And here, console.writeLine, dog.bark. So now I have an animal and then a dog. My dog is my derived class of my animal. So let's go ahead in my program. If I create an animal, animal A equals new animal, my animal has an age, a name, and it can move. And that makes sense. So let's go ahead and run that. And we can see animal.move is displaying. If I create a dog, dog D equals new dog, D dot, we can see we have age, bark, move, and name. Even though in the class definition for dog, no age, name, and move were programmed in here, but because it's inheriting from animal, and it inherits all the characteristics of animal because it creates this is a relationship. A dog is a animal now. This is the same thing that we did before with the interfaces. When a class implements an interface, it had to the interface kind of forced it to implement its own implementation of the interface. This is sort of the same way, but now we get to kind of derive the implementations. We get to have the implementations of the animal class in our dog class. So yeah, I have dog dot, and I can do all the things. Now, anywhere I see a function, static void move animal, taking in an animal A, anywhere I can see this, I could do, a dot move, right? But I could pass in my dog to this function because my dog is a type of animal. So when I run that, now we have animal.move twice because I called move twice. Yeah, so I could pass in my dog to this animal, or this function that requires an animal, because a dog is an animal. So this is a basic hierarchy with animal and dog. This is a base class, derived class. Okay, let's talk about changing behavior with this kind of setup. Now, so when we're building a class hierarchy, sometimes we'll want to, not only extend the behaviors of the base class, but we might want to replace them and modify them to make, maybe our derived class more specific. So, for example, right now, if I go, let's remove this. If I go dog D equals new dog D dot move. When I do this, I get animal dot move. Even though it's a dog, it's saying animal dot move. It's not specific enough for me. It should be able to say animal or dog dot move. So I can override this move function from the animal class to specify my own behavior for this specific instance of dog. So to do that, I would mark my move function as virtual. And by marking it as virtual, this now allows me to override this function in any derived class. So if I take public override, we can see I can override move now. And now I could provide a different kind of behavior for it. Now I could say console.writeLine dog.move. Now basically what's happening is when I run this code, now it's going to say dog.move because I'm calling the dog version of this. Basically, it's when you override the function of a base class, it uses the overrided version of the derived class. And this allows you to just make it more specific for your class. So I don't want it to say animal.move, I want it to say dog.move. So I override this move, and now I can write my own behavior. Now, what if I just wanted to, keep the old one, but then just add to it? Well, I could do that also. I could just, in that case, say base.move. And by doing that, I'm saying, okay, override move, but still do the same move that it does now. So it's base.move or baseclass.move. So it calls this one, and then it does my own custom behavior that I added. So now when I run this, now I'll have animal.move and dog.move like this. Animal.move, dog.move. Yeah, so by using virtual and override, I can change the behavior of a virtual function in the base class in the derived class to maybe add things to it, to completely remove it so it does something different, and things like that. Okay, so if a base class doesn't declare a method as virtual, a derived class cannot override the method. So you can only override functions or methods that were defined as virtual. Now, this leads me into listing 2-48 inside of this chapter. I've looked at this a couple times, and it's completely wrong what they're saying in listing 2-48, unless I'm wrong, and if I am, someone correct me. But I learned programming in a completely different way, apparently. But I'm pretty sure they're wrong. Let me read what they're doing here. I'm going to read essentially the paragraph above this 2-48 to show you what they're trying to do. So it says, if a base class doesn't declare a method as virtual, a derived class cannot override the method. It can, however, use the new keyword, which explicitly hides the member from a base class. This can cause some tricky situations. So what they're saying is we can use the new keyword, which explicitly hides that member they're using the new keyword on from the base class. And pretty much that's incorrect. That's not true at all. Unless I'm wrong, which, like I said, someone correct me. Using the new keyword is used for hiding a method. They are correct with that, but it doesn't hide the function that, or as they say, it doesn't hide the member from the base class. It hides the base class function. Rather. So I'm going to go ahead and write their example and then show you what I'm talking about. So in their example, they have a class called base, base. Inside of base public void, they have a function called execute, which just writes to the console saying base dot execute. That's the execute of the base. Then we have class derived, which implements or inherits from base, and derived just says public new void execute. So this is where the new operator is coming in. And now, like I said, when you use new like this hides. What am I doing? Console.writeLine derived. That's what I get for trying to copy and speak. Derived.execute. Okay. Now, when you use the new keyword, like I said, what really happens is it hides the base class implementation, so that you can use a function with the same name that's in the base class. And I'll show you what I mean by that. So that's that. So let's go ahead and create inside of my main. Let's go base b. This is what they did, by the way. I'm just copying what they did right now. Base b.execute. B equals new derived, and then they do b.execute again. They run this, and we get base.execute, base.execute. And from what they did, they're saying, okay, look, we got base.execute 2 times, even though the second time we created new memory and we set the b is equal to a new object called derived, so that it should call this execute, derived.execute. So they're saying that the new keyword, because it doesn't get that output, they're saying the new keyword is causing it to hide the member from the base class. So they're saying the new keyword is hiding this function from the base class. That's what they're saying, which is not correct. And maybe I'm reading this wrong. Like I said, if someone has the book, look at listing 2-48 on page 130, and they can tell me what they think about this. But basically, the reason why they're getting this base.execute to display twice is nothing to do with the new keyword. It has to do with because when we say base b equals new base, b.execute, that's normal. But when we say b equals new derived, yes, we're allocating memory for this new object that's of type derived, but we are looking at that object through the eyes of a base class. So through the eyes of a base class, we're looking at it as a base. So we only see this base function, which is base.execute. So because of that, the base.execute function is being called. And that's why we're getting it 2 times. If we casted derived, you got it, and then did b.execute, we would get the derived.execute like we properly would. But it's because we're accessing it through the eyes of the base class. Now, to prove my point, let's go ahead and just mess around with this. And if I remove this, recompile, I was getting a warning already, and I highlight this warning. The warning says, so this is without the new keyword. Lesson 2-4. Derived.execute, which is this function, hides inherited member base.execute. Use the new keyword if hiding was intended. So look what it's saying. It's saying the derived.execute is hiding the inherited member base.execute. Derived is hiding base. Now listen to this. The book says the new keyword or whatever, which explicitly hides the member from the base. So this is saying the book says hide member from base. This is saying hides base from hides base from derived. So yeah, this is saying it's hiding the base from the derive. So pretty much what it's saying is, because if you have a function in the base class, it's called execute, and a function in the derived class, it's called execute, it's going to use the one in the derived class. Pretty much the one in the derived class is hiding the one in the base class. It's not going to see the one in the base class. And to prove that, if I go derived d equals new d, derived d.execute, as you can see, we get derived.execute. So this is what it's doing, and this is not a problem. It's issuing us a warning, and it's saying that we should just specify it as new. It does not change anything. It just makes the warning go away. Now, when I run it again, I'm still going to get the same exact result, derived.execute, except the warning just went away. So even with this, like I said, we get the correct behavior now. We're getting the derived.execute rather than the base.execute because we're accessing it through a variable type derived. If I had base b equals new base, then b equals new derived. I don't know why I did that. I could have done base b equals new derived. But b.execute, I'm going to get the base.execute because I'm looking at it through the eyes of base. It only sees the base function, essentially, what's happening. So yeah, that's what new does. So the book, I don't know. Correct me if I'm wrong, but the book is wrong. Once again, the book says, using the new keyword, which explicitly hides the member from a base class. So it's saying it's hiding this from the base class. Well, it's not true. This is hiding the base function from the derived class. It's hiding it. So yeah, like I said, take a look at that. So yeah, this is the correct way. Using the new keyword hides the base class function so that you could use a function with the same name that's in the base class if it's not virtual. So if you want to create if you don't have if the function in the base class is not virtual and you want a function with the same name, you can mark it as new, and it will just hide the base one. It will use the derived one. That's what the new keyword is really for. But even if you don't put a new keyword, it will still work the same way, but it will issue a warning to you. That's it. So yeah, this is the correct way to do it. The book is wrong. Listing 2-48 is not correct. Okay, so moving on. So there's another feature, or a couple features that we have with this kind of stuff. We can mark classes as abstract, and we can mark classes as sealed. So basically, if we don't want to allow a base class to be instantiated, meaning that the base class is only there to be used as a base class. It's never there to be used as on its own. So an abstract class cannot be instantiated. It can only be used as a base class. You could declare an abstract class. This is what the book says. Blah, blah, blah. An abstract class can implement or have implementation code for its members, and it can also not have them. So it's not required, and you'll see what I mean by that right now. So let's go ahead and create an abstract base class. I want to mark this as abstract. And inside I'm going to have two function definitions. The first one I'm going to say public virtual void method with implementation. And it does something there, whatever. Public. Now this function I want to mark as abstract method, and notice how I do not supply an implementation for this. So if I have an abstract class, if I have a function in it that's marked virtual, that's not actually if I have a function that has an implementation, that's fine. But if you have a function that's marked as abstract, you do not supply the implementation. Rather, the derived class has to implement it itself. So by doing this, it's basically a nice way that we can share both. We can pretty much share an interface and implementations. So basically what this is saying is the derived class, what's a good way to say it? The abstract class is acting as an interface with regards to that it has an abstract function, meaning that the derived class must implement this abstract function. It must implement it. But if you supply a function with an implementation, then the derived class will just inherit that and have it. So in this, I'm just gonna. Oh, I can't do that with that. I'm just gonna implement this public um, override void abstract method. Okay, whatever, that's fine. So basically, if I compile this should, yeah, okay, it compiled fine. So basically, if you have an abstract function, you have to override it or implement it. And this is just the syntax for it. We have to implement it in the derived class, so we override it in the derived class. And we didn't override this one because the implementation is given here, and then we just we inherit all those we inherit the implementation for the derived class. And then just on the side, I just want to note that a sealed class, if you mark a class as sealed, it just prevents it from being derived from. So an abstract class cannot be instantiated, a sealed class cannot be derived from. Structs are implicitly sealed, so it's never possible to inherit from a struct. So a good exam tip the book's giving is make sure that you know the difference between an interface and an abstract class. An interface has no implementation code. An abstract class can choose to implement methods or leave it to the derived class. So it's saying an abstract class can implement methods or not implement methods and force the derived class to implement them, like we see here, by overriding it. Okay, so the last section of this lesson is implementing standard .NET Framework interfaces. I'm going to try to go through this pretty quickly because, I don't know, you guys can look this up. This isn't, I mean, it's pretty important, but I don't know. So .NET has interfaces that we can use on our custom-defined types that we create. And basically the benefit of using the .NET standard interfaces is that we can use, once our classes implement them, then our classes can be used in the infrastructures that .NET Framework offers. And what it means by that is, for example, the first interface is IComparable. And by making a class that implements IComparable, it allows that class to be used to sort things. So we can use the built-in list or array sort functions if our class implements IComparable. And I'll show you what I mean by that. So let's go ahead and create let's make a class called student. And this student class has a public, what does it have? Public int ID. Has a public int ID. This is what our student class has. So if we take this and let's say we create a list of students. And then we go, students dot add new student ID equals 2, ID equals 3, no, that's 50, no, let's say 5, 3, 4. So we have a list of students, and our students are in it, and the IDs are 5, 3, 4, respectively. If I try to go students.sort, and I want to sort my students, we get a problem. So basically, let's sort it. Now let's display it. So for each var x in student console.array line x.id. So let's see if it worked. And okay, and we get a problem. So we get, let's see the error. Invalid operation exception, failed to compare two elements in the array. At least one object must implement IComparable. So this is what it means. The book means by that. If we implement .NET's interfaces, we can use the infrastructures that are built into the language. So this sort function is that infrastructure, and we want to sort our things. But if you think about it logically, if I try to sort these students, if I don't tell it how to sort, how will it know what to sort? If I say students.sort, how should it sort it? It's just a student, has no idea how to sort it. So we have to specify sort it based off of ID. And that's what we need to do by implementing IComparable to our student. So if I implement IComparable, I'm going to do the generic one. So there's generic and non-generic functions. And I'm going to implement this interface. So I just implemented it, and that there's only one function that we have to implement, which is compare to. And basically what I'm going to do is, because int is a .NET or int is built into C#, it automatically implements iComparable. So I don't have to worry about it. So I can take advantage of that to make this work. So I'm going to say return this.id compare to other.id. And basically what it's doing is the compare to function that's built into this class will basically do one thing. It will check if it's less than the same value or greater. Depending on what it is, it will return less than 0, 0, or greater than 0, and that's why it's returning an integer value. And because of that, now our class can be sorted because it's sorting on the IDs. It's calling this compare to, and it's saying is this greater or less than whatever. It returns them, it does some things behind the scenes, and ultimately it can sort them now because I'm telling it to sort on the ID. All because I'm implementing this interface iComparable. Now if I run this, look what happens. We get that 3, 4, 5. So my students were sorted out basically based off of the ID that I supplied right there. So that's iComparable. Okay, the next interface is innumerable. And innumerable is an interface in .NET that helps you implement the iterator pattern. The iterator pattern allows us to access elements in a collection without caring about how exactly it's implemented. I was reading from that book. So basically, when we implement innumerable, that essentially allows us to it's basically implementing an iterator that allows us to then basically use a for each loop. Because it allows us to use a for each loop on some kind of data. For example, let's create a class called. Actually, let's bring back our student. So we have a class called student. Let's create a class called, I don't know, classroom. Inside of classroom, it has I guess we'll do an array called students. And there's only 3 students in our class. Let's just say student sub 0 equals new student. ID equals 1. So we have a student array, and then we have 3 students, 1, 2, and 3. Let's override toString so that it returns the ID, and it prints the ID for each ID. So it prints the ID for each student. Now think about this logically. Let's say I wanted to use a for each loop with my classroom. So I have classroom r equals new classroom. So now behind the scenes we have all our 3 students. If I wanted to say for each var student in R, how would I do that? Basically right now I can't. I want to display all the students in R. How would I do that? Or display all my students in my classroom? Basically, I want to use this for each loop. So essentially, we need to kind of implement an iterator or some kind of mechanism that kind of sends the values of the array to the caller. And by implementing innumerable, we're allowed to do this. Now, there's a listing -2-55, which just shows basically what the for each statement or for each loop is doing behind the scenes. and it has move next, current, and stuff like that to keep and maintain state. And we're going to see that here in a second. So basically, in our classroom, what we need to do is we need to implement this innumerable interface. So innumerable of students, let's say the generic one, and then let's right-click implement interface. Off the bat, we get two implementations two functions that we need to implement. The first one is a generic get enumerator, and the second one is the non-generic get enumerator. This one is simply just going to call or return get. It's going to call the generic one. So if you're using a non-generic interface, we'll call the generic interface automatically. But we still have to implement this generic interface. So how we're going to do this is interesting. We're going to set up a loop for int I equals 0 as long as I is less than students.length I++. Here's a new keyword. Yield returned students sub I. So basically, actually, let's go back to here. Let's try this now, just so you can see how it works. Student. Let's run that, and we get the IDs 1, 2, 3. So we're seeing all the students inside of our classroom by doing this. So basically, what's happening when we're implementing this innumerable interface? This get enumerator function is called when we enter this for each loop. It calls get enumerator. And the job of the enumerator is to enumerate or iterate over our internal data structure, so our internal array that we have set up. It's going to iterate over that and call this yield return. And this yield return basically allows you to send the value back to the caller, so back to the for each loop, give it the value, and then stop. Then when it wants its next iteration, it will come back to this for loop to get the next value and start off where it left off. Now, it's able to pick up where it left off because this yield keyword does all things behind the scenes by creating that move next function and the current property so that it knows how to maintain state. This yield keyword basically allows you to maintain state, and it knows where it is. It remembers where it left off so that it can pick up right where it left off. So basically, if I were to put a breakpoint in here and run this, and I were to step through this, when the for each loop starts, we'll enter the get enumerator. Sorry, I just had to disable. It was taking screenshots from hitting F11. So it enters the enumerator. It enters this for loop. We hit the yield return. Look what happens. It goes back to the for each loop. It prints that return, which was 1. It goes to the toString. We can keep on going. So then we get to the next iteration of the for each loop. It comes back into the enumerator. So it remembers its state. It remembers where it left off because of this yield word. And it picks up where it left off. So every iteration of the for each loop, it's going back into this iterator or this yield return and it's getting the value. So that yield is maintaining state. So you may be saying, okay, why not just create a list and put all the values into a list and then return the list so we don't have to use this yield stuff? And yes, that works. But it's just creating more overhead, essentially, because we're creating that new list, which remember it has to be managed by the garbage collector and everything. So we have a list. We have a list here. We have a list that we're creating and returning, and that all has to be managed. For ultimately, even if we just return the list, when we do the for each on that list, somewhere behind the scenes, it's still doing this yield return to actually get the data from the class to the caller. It has to do this yield return. So basically, by implementing this yield return and this get enumerator ourselves, we can skip the hassle of having to create that overhead with that extra list or something like that. Um, okay, so that's basically it. I'm gonna skip over iDisposal and iUnknown. Just look them up. They're pretty basic things. iDisposal is dealt with cleaning up unmanaged resources, and iUnknown is used for com. So that's it for this lesson. I went fast towards the end because this video is getting really long. So if you have any questions, let me know, and I will try to answer them. Alright, thanks for watching.